Thank you very much, Professor Yan, for the introductions, although I do not understand fully, but I'm sure that it's a very good introduction. So, good morning, ladies and gentlemen. It's a great honor for me to be here at this China University of Petroleum. And I was also this morning made the honorary professor for this university, and I feel really honored for that as well. So today I'd like to talk about a topic called harnessing solar energy through catalysis. And as you can see, that my name is Amal, and that is the name that I'm known professionally. That is the name that's listed in my high school certificate and also my degree. But for my mother and father, I'm known as Amal张露晶. So my grandfather was from China. He's from the province of Fujian. I was born in Indonesia, and after the talk, if you want to talk a bit more about my history, I'm happy to do that. So, harnessing solar energy through catalysis. I think you agree with me that nature has been very good in terms of harness the solar energy through catalysis in order to sustain life on Earth, and that's known as photosynthesis. But today's talk, I'm going to sort of give you a little bit more of my perspectives of how we will be able to capture the sun energy in different ways, and how then we will be able to use it for good applications such as for chemical reactions, for energy applications, for water treatment, and for environmental applications as well. But before that, I'd like to introduce you about my university. So where we are and who we are. So I'm from University of New South Wales, now it's called University of New South Wales, Sydney. We would like to be known as the Australia's global universities. The reason is because we have many international students in our university. In my own school, we have about 46% of our undergraduate students are from overseas, and about 65% of our PhD students are from overseas. So you can see that we are really international universities. And we also would like to be known global universities because when our graduates finish their degree, when they go back to their country, they are the one who's going to be changing the world, making the world a better place. So we believe that our outputs, not just the outputs of our research, but our outputs are also outputs of our graduates. We are the School of Chemical Engineering, part of the faculty of Faculty of Engineering. And the Faculty of Engineering at University of New South Wales is the largest faculty. In 2016 alone, that faculty had 11,000 enrolled students. And we are ranked number 21 in the world and number 1 in Australia according to the QS ranking. So in chemical engineering, we have 26 faculty members. So compared to your colleagues, probably smaller. We have roughly about 800 students, so again, quite small. In our school, we offer 3 degrees. One is Bachelor in Chemical Engineering, another one is Bachelor in Industrial Chemistry, and also Bachelor in Food Science and Technology. We have roughly about 335 postgraduate students and about 120 PhD students. So in chemical engineering, we believe that it is important when we do research, is research that we will solve global issues. So those issues that we believe that are important globally are including the energy, water, food, and health. So those are the areas that most of my colleagues and I sort of focus on, and we working in the areas not just at applied, although it's a chemical engineering, but research is also about discovery science. So if you look at our research, it varies from sort of molecular understanding through to materials discovery and advanced process engineering and product and development. And we also in the school, we have quite a very good facilities. We have facilities such as the computational resources and visualization. We also have laboratories, analytical facilities as well, and also some pilot scale process integrations. So because it's chemical engineering, so we believe that it's very important to have the integrations between science and engineering. So chemical engineering it's a great place or a great discipline to be able to integrate or to interface between the science and the engineering. And for those who are interested to do PhD in our school offer research degree, high degree research, master research, and also PhD. And those are the areas that we offer in the research areas, in the areas of energy, environmental technology, food health and medical science and technology, macromolecular and interfacial engineering. So the macromolecular and interfacial engineering, that is more the polymer or protein engineering, and advanced product and process engineering. So you can see that it's quite a number of different areas that we cover in the areas of our research. Before I start the topic of my presentations, I'd like to first acknowledge also my past group members and my present group members. These are my present group members. This photo was taken Christmas in 2016, and one of the students in our group, Pat is Wu Hao. Not sure whether I can find it. That's the one. Wu Hao is from this university. He did his master's here, and then he spent about a year in our laboratory as an exchange student, and now he's back. So as you can see from the pictures that the group consists of different students from different countries, mainly from Southeast Asian countries and also China, and we also students from Middle East and locals as well. So it is quite a large group. We have 3 academic staff members in my group, which is called Particle and Catalysis Research Laboratory, and we're working in the areas of from energy conversions and as well as energy storage. So looking at catalysis, looking at particle agglomerations to battery areas as well. So going back to the topic that I'm going to cover today is harnessing solar energy through catalysis. I already mentioned that nature has been very good in doing that, and that is the process which is known as photosynthesis. Without this process, I believe that life will take a different path. So how can then we, as a human being, be able to also do the same and do it more efficiently to harness the solar energy and then convert it to chemical energy? The electrical engineers have been very good to do that. That's why they've got a lot of these solar panels on the rooftop or solar panel in the power plant in order to convert sun energy to electrical energy. But as you know, with this type of process then, with the solar panel, when there is no sun, there is no electricity. So we as the chemical engineers can perhaps even do better. Can we actually, using our strength, using our skills, to be able to harness the solar energy and then store it as a chemical energy? And one thing that I'm going to cover today is that to sort of see how we can look at different ways in order to harness the solar energy through catalysis and store in chemical energy. Because if you look at the, perhaps in terms of solar panel, mainly they focus on the UV and the visible light. But there's also a huge spectra, which is the infrared, 52% of that. That is the one that normally causes the heat. So like today, the weather is hot, that is a lot of based on because of the infrared radiations rather than just the UV or the visible light. So how can we capture all those spectra in order to be able to drive our chemical reactions? Today, what I'm going to cover is that looking at the sun radiations, which is from the UV visible infrared, how we can use the photon. So photon is the light, and then using the light in order to activate the catalyst to drive the chemical reactions, or the heat of the sun, the thermal, and then store that or activate using that energy in order to activate the catalyst and to drive the chemical reactions. And another one is that indirectly. So we know that solar energy can be used in order to convert it to electricity. How can we then indirectly, using that sun energy, create electricity, then we use this in order to drive the electrocatalysis. So my talk today will cover the photocatalysis and then the photocatalysis, the photothermal catalysis, as well as the electrocatalysis. For the harnessing solar energy through catalysis to drive the chemical reactions, the one that most widely studied, mostly sort of researched, is in the areas of photocatalysis. So from the name photocatalysis, it means that we're using the photon of the sun energy and then use that in order to activate the catalyst for the reaction. And it's well known, and a lot of people doing the research is because they can see the different applications. This photocatalysis process can be used to treat water, to purify air, also can be used to synthesize chemicals. So using the sun energy to use it for organic synthesis, and more recently people looking at for hydrogen generations, for reforming, as well as for CO2 conversions. What I'm going to do for the next few slides, so my apology for those working in photocatalysis, because it might be something that you already know already, but because I know that the audience is coming from a diverse background, I'm just going to explain how the photocatalysis works. So for these catalysts, normally they are semiconductor materials, because the semiconductor materials, if you excite it with light of energy greater than the band gap, you will then have the so-called electron hole pair. So what happens is that when you hit it with the sunlight, and for the semiconductor that has a band gap that is suitable for the sunlight activation, you got the so-called electron and hole pairs. So you excite the electron from the valence band of the semiconductor to the conduction band. Therefore, then you will have electron and hole pairs, and the holes will then react with the water molecules to form hydroxyl radicals, and the oxygen will react with the electron to form the oxide, superoxide radical, which is activated oxygen. And these two activated oxygen and hydroxyl radicals are highly oxidizing, which is then when you have a pollutant such as organic in water or pollutant in air that will be oxidized to form carbon dioxide and water. And the organic itself can also react directly to the holes in order to organic itself can react with the holes in order to be oxidized to the carbon dioxide in water. So this is the process if you wanted to use this catalysis in order to oxidize or to clean water or to clean the air. You can also using the same science, the same sort of principle in order for water splitting, in order for generate hydrogen. So what it does is that the same things you will got the electron and hole pairs, the water will then react with the holes to form the oxygen gas, and the proton will then react with the electron to form hydrogen gas. As we know, hydrogen gas is an energy carrier for the clean fuel, and you can use this as a source for the fuel cells to drive electricity. So we can store the sun energy to chemical energy, which is the hydrogen, in order to be able to drive the fuel cell. The applications that you can also use the photocatalysis is for carbon dioxide reductions. For me, this is a holy grail reaction. This is artificial photosynthesis, where if you got only the sun and the carbon dioxide and then the water, you can really actually convert this water and carbon dioxide to methane for natural gas. So it's the same principle. You got the holes reacting with the water to form proton, and the proton react with the electron to form the hydrogen radicals, and then react with the carbon dioxide to form methane. I was just talking with Chetan this morning about how my research related to sort of your university, which is University of Petroleum. And I believe that what I'm talking about today is just one alternative I still believe that I think we still need to work on the fossil fuels, technology and research. And even with this technology, I guess ideally that when we use fossil fuel, we will not able to really, we will still produce carbon dioxide. So the carbon dioxide that we produce, instead of we emit it to atmosphere, we probably can capture it and then convert it to something valuable. So this is something that I see as a complement to whatever the fossil fuel research that we're currently doing. I'd like to show you this particular graph. This is a statistic that I got from ISI Web of Knowledge about photocatalysis and photocatalyst research. The reason I show it to you is because photocatalysis research was originated or made famous, I have to say, by the Japanese group back in late 60s and early 70s. So it's by a group from University of Tokyo, by Professor Fujishima and Professor Honda, when they discovered that they can use titanium dioxide in order to, when the titanium dioxide was illuminated with light and put at the anode, they can produce hydrogen at the cathode. So since that particular discovery, a lot of the Japanese university and Japanese researchers were investigating how we can use this photocatalyst and how to use this catalyst to harvest the sun energy to convert it to chemical energy. And as you can see, back in the 80s and 90s, the Japanese is actually leading in the area. But in 2004, we can see the research in photocatalysis actually took off in China. The number of publications in photocatalysis and photocatalysts in China is actually exponentially increased. And you can see also the difference in terms of the publications number from China compared to other countries as well. And that is an area that people are really interested in, because I guess that the ideas of to be able to use sunlight and CO2, which is a waste, and water, which you can get from ocean, you can convert it to hydrocarbon that you can use as a fuel or can use as a chemical feedstock, is very interesting or promising as well for the future. And the reason I want to show you this graph as well is because with the publication from China particularly, a lot of the research are in the areas of photocatalyst design. So when we talk about photocatalyst research, I would say that you can divide it into three types of research. Photocatalyst design, so 90% of the research in the, that published in China are in the areas of photocatalyst design, and less than probably about 5% or less will be on reaction mechanisms, and then on reactor system engineering. And so one of the messages I wanted to sort of say later on in my presentation, which you can see, is that it is very important to have the integrations between the photocatalyst design, reaction mechanisms, and reactor system engineering. So the first part of the research in the photocatalyst design, so when you design a catalyst, whether is it for the water treatment, for air purifications, for water splitting to produce hydrogen, or for CO2 reductions. These are the three things that people use as a criteria when they wanted to design a good catalyst. In the cartoon that I showed you earlier, when I said that the photocatalyst, when you excite it with sunlight, you can produce the electron hole pairs. One thing that I forgot to mention is that those electron hole pairs can be combined very quickly. The time scales of the recombinations of the electron holes are 3 orders of magnitude faster than the electron transfer process. So when you design the catalyst, it is very critical of how to minimize the recombination. So a lot of effort in the photocatalyst design they put into that. Another thing is that the reactions happen on the surface. So also in the design, you have to design in such a way that you can promote the charge transfer very efficiently. So that's another criteria that you use. The last but not least that people use to, as a criteria to design the photocatalyst is that it would like to absorb the wider solar spectra. I showed you the solar spectra earlier, that it consists about 5% of UV radiations, about about 40% of the visible light and about 50-something% of the infrared. So a lot of the photocatalyst design is they wanted to not just utilize the UV part, because the most active catalyst is only can be activated by the UV part of the sunlight, but they also wanted to be activated by the visible light. And the work that we're doing currently in our lab is actually extend it further, is to see how we can use the heat, the infrared, in order to be able to activate the catalyst. Because we believe that 50% of the, or more than 50% of the sun radiations is the heat, and we should be able to capture the heat in order to drive the catalysis. Okay. So what are the strategies in order to meet those criteria? One of the strategies that has been used, as probably one of the first strategies, is because it's quite simple, is the metal deposits. So you can deposit metal, if you're talking about the expensive metals, you can deposit gold metals or platinum metals on the photocatalyst, which one of the mostly what we use photocatalyst is titanium dioxide. And that metal deposit can help to minimize the recombinations of the holes and electrons. And also, it can act as co-catalyst, because we know platinum particularly is a very good thermocatalyst. And by having the platinum there, or even some of the work that we're doing now is having nickel or having copper, it can also act as a co-catalyst. Nanostructuring is very important. There's a lot of research looking into one-dimensional structuring, and now, more recently, two-dimensional structuring. I think one-dimensional structuring particularly is very good for the transport, but two-dimensional structuring, because it's very thin, and as you know that the reactions of catalysis normally happen on the surface, so what happens is that when you've got two-dimensional type of structure, you've got a very fast charge transfer to the surface for the surface reactions. The third one is mesoporous structuring. With the mesoporous structuring, it means that you're looking at making a very well-aligned pores. And one of the good things of that is that you have larger surface area, which is again important for catalysis reactions, but you also improve the light scattering. Just remember, with photocatalysis, different from thermocatalysis, the light is very critical. So the multiple scattering due to the aligned structures is very important in order to enhance the illuminations on the surface. The more sort of newer approaches in terms of making the catalyst more effective is the so-called defect engineering, or surface oxygen vacancy engineering. That is not just important for photocatalysis. For thermocatalysis nowadays are very important to create more surface oxygen, because those sites have been found recently, because of the in-depth characterizations that we do, to be the most active sites for a lot of the reactions, for CO2 dissociation, hydrogen dissociation, oxygen dissociation. So be able to design those defects on the catalyst is very important. I used to say that we would like to have perfect catalysts, but actually nowadays I said to my students, we want imperfect catalysts, because the defect is actually what we wanted for our surface reactions. Another one is the crystal facet engineering. So design different type of facets. We might have the same crystals, like for example in our case here is a bismuth vanadate, or in some other case is titanium dioxide. But we can actually design different crystal facets, and the different crystal facets actually have preferentially different type of reactions. Like for example, in the bismuth vanadate, the crystal facets of 010, it's preferentially going for reduction reactions, because it's more electron rich, while the 110 facets have less electrons. It's actually better for the oxidation reactions. So in our experiment, we sort of illustrated that. We can see that we see silver, which requires electron to deposit, to reduce it, will deposit onto the 010 facet, while the oxide that normally require holes or electron vacancy in order to oxidize it if it's deposited onto the 110. So fast engineering is also being used currently also for thermocatalysis, because they can see that the facets of the support is very important for the electron interactions between your support and your catalyst, your co-catalyst. When I was in the conference yesterday, people were looking at depositing copper on titanium dioxide and copper on the zinc oxide, and they found that the facets of the titanium dioxide and the zinc oxide are very critical in terms of affecting the reaction for thermocatalysis. And another one is the band structure engineering. When I show you the cartoon in terms of looking at how the semiconductor works, one thing that I did not mention is that the positions of the conduction band and the valence band, so the positions of the electron and the hole potentials are very important. So it's not just the band gap energy. The band gap energy dictates what sort of light that you can use to excite it, but the band potential dictates the energy of your electron and energy of your holes for your surface reactions. So band structure engineering particularly is very important in terms of looking at what reactions you require. For example, for hydrogen generation, so when you wanted to reduce the proton to hydrogen, you need enough electron energy in order to be able to reduce it. And if you wanted to oxidize organic, then you require enough, again, hole potentials to be able to oxidize it. So band structure engineering is very important in order to really design the right catalyst for the right reactions. So those are the strategies people use in order to design catalysts. In my group, we're using these three approaches. We use other approaches or techniques to synthesize our catalysts. The one that we are probably, can we say that, famous for is the flame synthesis. So we're using flame as the reactor in order to synthesize our catalyst. And one of the good things of the flame synthesis catalyst is that when you synthesize it, you can actually put in together your catalyst and your support. Say, for example, if you want to make copper on TiO2, you can put the copper and Ti precursors together, which means that you don't have to have a two-stages preparations method that you prepare your titanium dioxide and then you're using your impregnations or co-precipitation to put your copper. And another good thing of the flame synthesis process is although it's very high temperature, so the flame itself will be near the source here will be thousands degrees, but toward the collectors it's hundreds degrees. But the residence time is very short. So when the residence time is very short, what happens is that you've got a catalyst of very high surface area and have a lot of defects. And a lot of defects, what we found again in our recent work, that is very important for a lot of the even thermocatalysis reactions, for surface reactions. Another technique that we use, and it's also widely used in literature, is the hydrothermal precipitations. I call it as a pressure cooker experiment, because with that one you normally put pressure, put temperature, and you cook the particles a long time. And normally with that type of synthesis method, you've got very nice crystals particles. So for certain applications that you don't want defect, that particular method are more ideal compared to the flame synthesis. We also work on anodization method. So again, this is also our specialty. But that method is mainly for nanostructuring, particularly for applications when we wanted to make catalysts on electrodes. So with the anodizations more for electrochemical processes, you can nanostructure the catalyst that you want on the surface of electrode. Okay, so I'm not going to give you a lot of the results that we found, but I just want to highlight some of the things and also my view, my perspective in terms of these different applications. So for organic pollutant degradations, photocatalysis research has been there for over 30 years. And people always ask me, then, what are the outcomes? What of this? I can see that in terms of the outcome of the looking at photodegradations that has already been used is for self-cleaning coating technologies. They are buildings, I believe they are also buildings in China, but mainly in Japan and in Singapore as well. They have a building that they painted using these photocatalysts. And what they want is that so that it has a low maintenance type of effect, because it has a self-cleaning type of properties. And also in Europe, they have this church called the Jubilee Church in Rome, that also the walls were coated by the titanium dioxide, and that will help them, to reduce the maintenance cost for cleaning for those buildings. And in Belgium, they have these pavements that the bricks were mixed with titanium dioxide, and the purpose for that is in order to destroy or to reduce the NOx. So it's for sort of air purification type of things. Although this one is not using solar energy, but it's more for indoor, it's probably applicable for Asian countries, because we'd like to have a clean indoor. This is also another technology that's been commercialized using the UV lamp and photocatalysis in order to destroy the pollutants indoor. So there are, based on the research, there are applications in terms of looking at using photocatalysts for degradations of mainly pollutants in air. For pollutants in water, there are some sort of smaller scale type of units that people use for water treatment, but again, one of the limitations, I have to say, for photocatalysis in water treatment is the reactor system. Because with the photocatalyst, when I show you the cartoon, you require the light to activate the catalyst. So with the name photocatalyst, without light, with no reactions. So if the catalyst does not see the light, you cannot have the reactions, no matter how active the catalyst is. So the design of the reactors has to be in such a way that your sunlight can actually penetrate through to see, or the catalyst can see the sunlight. So in that case, then your reactors have to be sort of thin film. And for large-scale operations, that is pretty difficult. So that's one of the limitations currently with the water treatment. Is more, for me, that is the biggest bottleneck if you want to use photocatalysts to harness solar energy for water treatment, is in the areas of the reactor system engineering, not in photocatalyst design. I believe that the photocatalyst that we have, titanium dioxide, is probably the best catalyst that we can use for water treatment, because remember when I showed to you before that we require the right valence band potential, titanium dioxide is the ideal one. And also, when we wanted to use for water treatment, we want the catalyst to be stable, not corroding. So a lot of the photocatalysts that people sometimes claim in their work that can use visible light, the problem is that it might corrode in water. So I already mentioned it, that I think in terms of photocatalysis for organic pollutions control, the catalyst, I think we have that. We can still improve it, perhaps due by more sort of oxygen vacancy to get that, but the limitation is more in this area rather than the photocatalyst itself. Okay, the second applications that I mentioned is in the areas of hydrogen generations or water splitting. So it is an area that lots of studies being done the last probably 15 years, and the reason is because people believe hydrogen can be an energy carrier for the fuel cells, and if we can split water from water to become hydrogen and oxygen, that will be great, because then we got abundant resources of the hydrogen. But it's an uphill reactions. Uphill reaction means the change in free energy is 237, so it's quite a difficult reaction. And how do we do it? There are two ways in terms of harnessing the solar energy to drive the catalysis for hydrogen generation, or for water splitting, I should say. One way is the suspension system. So the first suspension system, that's photocatalysis, means that your photocatalyst is as a powder, you put it in water, and then you shine it with light, then you got your hydrogen and oxygen. There's a lot of research going on with that, but I have to say the applications using that particular approach is very limited. Because one of the things that the hydrogen produced, oxygen produced in one system, they will recombine. So it's not an ideal system for applications. For applications, I would say the electrode system will be more ideal. And this is the photoelectrochemical system where your catalyst is actually deposited onto electrode. And then you have the solar energy illuminated to it. So there are three, I would call it the three generations of the PEC system. This is the one that Honda and Fujishima used back in the 70s in order to illustrate that the titanium dioxide can be used in order to generate hydrogen. So in here, you got the titanium dioxide, which is the so-called N-type semiconductor that they deposited onto the anode, and then they illuminate with light, and then they can generate the electron with a bit of apply of potential, the bias, and then on the cathode side, then they generate the hydrogen from the water. Research nowadays is focused more, still have a lot of research in these areas, but the newer research is in these areas, which is the second generation and the third generation. There are lots of catalysts that can be used as for the anode side of the electrode for the oxidation reactions, but they are limited of the materials that can be used for the cathode side. So a lot of research going on to look at the semiconductor for the cathode side, and also something that it will be stable as well, because that is one of the problems to have stable sort of cathode for hydrogen generation. And ideally that is, we want an electrode system that has both the anode and the cathode. So this will be like a leaf that you don't really even need to put in any potentials or bias. So if you shine the cathode with the sunlight and the anode with the sunlight, the reactions can happen by themselves. So this is the ideal cases, and a lot of research currently focus more on that, is to discover the materials that they can use for both anode and cathode and to drive the reactions. Okay, for the water splitting reactions, the suspension system, which I mentioned that I wouldn't see that as a system that you can use in applications, but it's a system that has been researched a lot so that people can discover the materials that can use for the PEC system. So although it might not be applied, the photocatalysis system, but it's a system that we can discover the science and discover the materials that we can then use in order for the PEC system. And again, this research was pioneered by the Japanese group, by Professor Domain and Professor Kudo. They're from University of Tokyo and Tokyo University of Science and Technologies as well. We also worked with the Japanese researchers in the area, and with our work is that we include the reduced graphene oxide to improve the electron transport. And we see that with the graphene, we were able to use the graphene to transport the electron from one catalyst to another catalyst, which is in the two catalyst system, where you have the so-called oxygen catalyst, which is this one here to produce oxygen, and this catalyst to produce hydrogen. We use our graphene in order to be able to transfer the electron from one catalyst to another catalyst. Okay, I did mention that with the photocatalyst system, so split water, the applications will not be of existence. But if you want to use the system, suspension system, and using sunlight, there is applications for that. That will be known as the photoreforming. What I mean is that instead of splitting water, what we do is that we can use the organic that are produced or byproducts from, say for example, diesel productions like glycerol. We can use that, the glycerol, and with illuminations, and mix it with the photocatalyst like titanium dioxide, and have a co-catalyst like platinum, and shine it with light. So the holes will go and oxidize the glycerol to the carbon dioxide, and the electron will then use in order to reduce the water to hydrogen. So with that particular process, I see that there's an application. And one of the things is that we know that biomass, sometimes we can get it from waste, and we can oxygenate the biomass to oxygenate hydrocarbon. So we need the oxygenated hydrocarbon in order to do that, because we still need the oxygen here to produce the CO2. And so in that particular application, I see that there are potential applications. And I'm also working in these areas. We're working on designing catalysts for photoreforming, for reforming glycerol, for reforming methanol in order to produce the hydrogen. So we are hoping that the glycerol and the methanol are coming from biomass. And the example that I showed you before was using gold as a catalyst. And again, the cost of catalyst is very important. So in hydrogen generation, platinum and gold are still the most active catalysts. But in our work, we try to reduce the amount of platinum we use. So what we did was that we combined it with copper. So in this example here, I show you that with about 50% of copper and platinum, we are able to photoreform glycerol to form hydrogen. So what we found from our characterizations, index studies using XPS, is that, and also using theoretical calculations, is that when you alloy copper and platinum, you increase the electron densities of platinum. So when you alloy the transition metals with some of the noble metal, what happens is that you not just reduce the amount of noble metals that you need to use, but you can also improve the electron density and to make the catalyst more active. Okay. The third applications that I mentioned is on carbon dioxide, and for me, this is really the program that we are working on in our lab. Most of my students working in this area, we call it closing the carbon loop. And I believe that with the fossil fuels in Australia, we still use coal as the main source for generating our power. We emit a lot of CO2. And I think with the CO2 that we emit, instead of just discharge it to the atmosphere, we can capture it and then we can convert it. So using sun energy to convert the CO2 and with water will help us to solve both our environmental and energy issue, which I call the closing carbon loop. But saying that, the CO2, as we know, is a very, very stable molecule. You got the double bond of carbon with the oxygen. So it's very stable, and in order to reduce that, it requires multi-electrons. Some of them, depending on the products that you want. If you wanted to get to methanol or ethanol, you require 8 electrons. So multi-electron, multi-hole, and multi-proton processes. So it's very difficult. You remember when I spoke about the uphill reactions of hydrogen-water splitting? With this one, the change in the Gibbs free energy is even higher. So it's a tough reactions to do. And even tough reactions, but because it's a holy grail process, people really wanted to be able to do that, and a lot of effort has been done in order to study that. Starting around early 2000 and 2005, a lot of people put a lot of effort using photocatalysts like titanium dioxide, that was earlier explained to be a very good catalyst to oxidize organic, in order to look at how they can be used for CO2 reduction. Our group also tried that, but we were not successful in order to get the CO2 reductions. What we found later on is that people sort of say that even including these particular papers, is that the artificial photosynthesis over crystalline titanium dioxide based catalyst is that fact or fiction. The issue is that when they're using titanium dioxide with some co-catalysts like copper, what they found is that they can produce some hydrocarbon like methane, but in a very, very small quantity. We're talking about 0.001 micromoles, almost non-existent. And so the question then is that real? Is that those hydrocarbons that were produced is actually coming from CO2? So what they found later on by this group of people, not just these two papers but quite a number, is that those hydrocarbons that produced by TiO2, I'm not saying that all photocatalysts, but some photocatalysts by TiO2 is actually from the residuals of the carbon on the surface of the titanium dioxide or the co-catalyst when they synthesize. So in this particular example here, it was published in Applied Catalysis B using the carbon-13 as isotope. So what happened is they labeled the CO2 with carbon-13, so that's the one. And then they're using titanium dioxide and metal. And what they see is that the methane that's produced is actually doesn't have the carbon-13 label, which means that it's not coming from the CO2. So, and they did some experiments with looking at different catalysts making synthesized from different methods. Some of them have more residuals of carbon than the one that left. The one that has more residual carbon seems to give you more methane than the others. So the conclusion from the isotope labeling and also the systematic studies of a sort of support with different residuals, they concluded that for that particular catalyst system, the methane that produced is not coming from the CO2 reductions, but it's coming from the carbon residuals during the synthesis method. So the message I want to sort of say is that, yes, it is a holy grail reaction, but we need to be very careful when we try to using photocatalysts, for example, especially that TiO2, which is highly active catalyst for oxidization, because the methane produced definitely can go back to the CO2 as well. So we should be very careful with that. So failing that, our group looking at capturing the other part of the energy spectrum of the sun in order to activate this particular, or using sun energy in order to convert carbon dioxide to hydrocarbon. So we're using both the light, the photo, the thermal conversion of CO2 to hydrocarbon. This is a paper that we recently sort of published in Engineering Journal. What we did in this experiment is we have nickel. Nickel is known as a very good catalyst for methanations. We put the nickel on titanium dioxide, also on mixed oxide support ceria titania. And what we did was that we put our catalyst here and illuminated it with light source that's around about 2 to 3 suns equivalent. So we did not supply any other heat. So the heat from the for the reactions is mainly coming from the light source of 2 to 3 suns equivalent. And what we found is that depending on the support, we have different methane productions. When we use nickel deposit onto a support that consists of 80% more of ceria and 20% more of Ti, it has the highest performance in terms of methane productions. We can produce roughly about 4 millimole per about 1.5 hours, which is very substantial, which is very significant, and we see also the pressure changes. So it is a real methane production from that. It's not due to carbon residues. And what we found as well that some catalysts, nickel on TiO2 and nickel on ceria, do not really produce the methane. So we did some studies to understand why, because that is part of the research, is to understand and to answer the questions why that, so that we can design even better catalysts. What we found is that the support play a critical role in terms of dispersion size of the nickel. So here we have done the nickel size, and you can see the one that most active is the one that has the smallest nickel size. And not just that, and it's important, I mean the ceria also have a nickel size that is small, but the nickel size is also the support also needs to be able to have enough defect in order to maintain the nickel size to be small. So that is a critical thing, that why the ceria TiO2 with 80% and 20%, because the ceria TiO2 of that configuration have the right defect size to be able to give us the right size and to maintain the nickel size at that small. And therefore that we can see the huge performance of this particular catalyst. We also did, this one hasn't been published yet, but we are in the process of writing, is instead of just nickel on TiO2, we also put lanthanum oxide. So it was synthesized by a combustion method with lanthanum and nickel. If you can see from the TEM and also the mapping, you can see you've got this nickel here, the red colored nickel, and a very thin, you can't really see it clearly on the projector, but a very thin green color lanthanum sort of coating on the TiO2. So we got this lanthanum oxide TiO2 process. And if you look at the activity of the reactions, this particular result was not done in the reactors that I showed you before, which is using just the light source in order to activate the reactions. We also have another reactors that we can use separately thermal and separately light and together as well, because it is important for us to be able to separate the effects of light and the effects of thermal, because we know nickel is a good thermal catalyst anyway, but we wanted to know what's the effect of light in that reaction. So if you look at this result here, NLT is the nickel deposit on lanthanum and titanium, LT is lanthanum titanium without nickel, and NT is just nickel on titanium dioxide. If you look at the result, the nickel lanthanum titanium is the most active one. It can, you can start to see the CO2 conversions or methane formations at temperature around 150 is the onset temperature. So why then the lanthanum help, and why then if you look at the nickel lanthanum you can see the effect of the light. I mean, the black one is the dark, so at 200 degrees the nickel lanthanum is not very active, but at when you have shine it with visible light or UV light, you can see that the CO2 conversion is actually kick up to 20%. So you can see there's a light effect for that particular configurations of catalyst. Why is that then? So we did an in situ drift, which are very small here. What the in situ drift sort of shows that is that when for your system when you have nickel and lanthanum TiO2, what happened is that you got the lanthanum oxide is good for carbonate formation, carbonate absorption. So the carbonate absorbs very close to the nickel lanthanum the interface here. And then when you excite the catalyst with light, nickel is actually it's called plasmonic metal as well. With light that is even less than 760, nickel will generate electrons, and this electron will help to dissociate the carbon dioxide to carbon monoxide into the nickel system. And nickel is also again a very good catalyst for dissociations of hydrogen. Therefore, that you've got this hydrogen and CO close by, and therefore from the methane. And as you can see here, at high temperature, you do not see much of the effect of light. So effect of light only important at low temperature, which is really ideal for solar photothermal process, because when we're using sun energy, we don't want it to use a very huge solar concentrator. We just want the temperatures normally, ideally it will be around 200 to 300. So it's an ideal temperature to be able to capture the sunlight in order to drive the reaction. But at very high temperatures, the reason you don't see the effect is that high temperature, you can, by itself, the temperature can dissociate your carbon dioxide to the carbon monoxide already in here. So therefore, you don't need the light. Okay. One of the other things that we talk about, which to use the different ways in order to capture the sunlight, the last one is looking at electrocatalysis. So it's more like indirectly using the sun energy. So we're using the sun energy to drive the electricity, and then using the electricity to drive the electrocatalysis. And I believe that this is one of the processes that it will have applications very soon. So for a short-term applications of sun energy to produce hydrogen, this will be the one, because there is already water electrolyzer, commercial water electrolyzer. What you have to do is to be able to match the solar panel type in order to be able to drive the electricity, because efficiency of those productions is greater than 10%. The competitions or the race among all the researchers that working in electrocatalysis is to design cheap catalysts. Currently, the electrolyzer, that commercial electrolyzer, the small one, they're using platinum carbon catalyst. And as you know, platinum is not cheap. So the race in research is to design cheap carbon-based transition metal catalysts for hydrogen generations. And our group is also working in that areas as well. Recently, we published in Advanced Sustainable System is to look at using nickel foam. So nickel is cheap. So what we did is that we pyrolyzed the nickel foam together with the metal organic framework of nickel and then graphitic carbon nitride. We pyrolyzed these three systems and we formed if you look at the system here, we've got a two-dimensional carbon with nickel nanoparticles. So here you can see, I'm not sure whether it's very clear, sort of nanosheets and some nanoparticles of nickel there. And we also did some theoretical calculations, because nowadays that if you wanted to publish your papers, if you have results, you have to really explain why. The editors, especially in Catalysis, good high-impact Catalysis journal, they would like to see either you got in situ characterization or you got some sort of theoretical calculations. So from the theoretical calculations, they revealed that the active site for the high efficiency of hydrogen generations, because we can have an activity similar to the platinum carbon here, is due to the combinations of the nitrogen doped carbon nanosheets that we have here, this nanosheet there, and also the nickel nanoparticles. So I'm not going to show you the video, but we also not just working in the lab scale, but we try to also upscale the system, and this one is still quite small, but what we wanted to do with this particular system, we want to bring it to the roof and then to use this in terms of to illustrate. So this particular system was, the electrode was coated by the catalyst of, that we make in our group. So if you look at the generations of the current, it's about 200 milliampere. I forgot to mention with the photoelectrochemical processes before, without not directly using the sunlight, in terms of the amount of current that you can generate, is still in the areas of microampere. So this one is a quite huge, 200 milliampere, and in this such a small system, we can actually produce about 1.4 milliliter of hydrogen per minute. So it's quite substantial, and for this tiny scales of electric system. And the applications, other applications that we use is for CO2 reductions. And what we see, this one is again, the application will be more limited, and because in terms of the yield of the carbon that we can produce, it's still quite low. But again, this is a very important area, because instead of we produce hydrogen, and hydrogen is still a bit hard to store because you need to have a good system to store the hydrogen. And if we can reduce the CO2 to a liquid product such as format as well as methanol or ethanol, that will be ideal. So recently we synthesize or design different type of catalysts, and depending on the catalyst, for example with tin and tin oxide, we can reduce carbon dioxide directly to format. And format, as you know, is a hydrocarbon that you can use as a feedstock for different sort of chemical products. And by changing the catalyst with the copper we are able to synthesize methanol and ethanol. So this one here to show that with different potentials, you can actually produce ethanol and methanol with different compositions. And to be using silver, which was published recently in Chemistry Select, we can produce carbon monoxide. So one of the systems that we're working on, which haven't really published yet, which is using carbon only, and what happened is using the carbon is actually doped we call it the defected carbon, we can produce carbon monoxide and hydrogen. So it's a combination of syngas. So we can tune in terms of the catalyst active site, we can make different ratios of carbon monoxide and hydrogen in this particular electrode system. So what we are hoping is that we can use that as a precursor of syngas that could be used for the hydrocarbon generations, like perhaps gasoline or diesels as well. And our school is currently building a very tiny, small pilot scale on our roof, on the building of our roof of our building, in order to look at how to integrate the different research that we're doing in the school in the energy area. So I already explained to you that we're working on the photothermal, so using the sun, light and the heat to be able to drive the electricity. We can use the solar panel and to drive the water electrolyzer, which we know that can produce a lot of the hydrogen. With this one here, it's still under investigation. I don't think we will be able to get the carbon monoxide and hydrogen enough to drive it, but the carbon dioxide from our methanation process that I showed before can be directly put into our solar thermal reactors. And then if you look at the ingredients, the sources of this is the carbon dioxide, water and the sunlight. So using sunlight and carbon dioxide and water, we are able to get the green hydrocarbon and the fuel and the chemical feedstock. So I think the take-home message, I think me as an engineer always like to think that when we do research, it's important to discover the science, but it's equally important when the discovery to be able to be translated to the real applications. So for harnessing solar energy through catalysis, I believe that it is important not just to look at the design of the materials or the catalyst, which I mentioned earlier from the literature. 90% of the publications are in the areas of the catalyst design, in the photocatalyst. I think it is important to be able to understand the reaction mechanism and the process system as well, because when we're talking about the reactions in the large scale, it is important to integrate the solar power to catalyst system, how to be able to bring the sunlight to the reactor and to activate it. Okay, before I end, I'd just like to draw your attention to a conference that will be held in Sydney, and this is a conference called Future Energy Conference. It's going to be held in University of New South Wales in February next year. So I think it's after your spring festival. It's in the areas of applied science and fundamental for alternative energy technology, so it's including the energy conversion, energy storage, and we'll also have industry days as well. So if you're interested in that, you can go to the website and hope you can join us. And thank you for the attention. This is a photo taken about a month ago. I was not in the picture, but it was a picture taken during a graduation ceremony or after the graduation ceremony of four of my PhD students, and Wuha was here too. I was in a meeting and I couldn't join them during the picture time, but our group are a very happy group and very productive group as well. So with that, I thank you for your attention.